think we can start. Uh, so last week we uh, discussed on the shear stress from the Hooke's law, the Poisson ratio, and then some example on the Poisson ratio, finding the strain, and yeah, next week Tuesday we have a quiz, and so far the quiz will be only chapter 1. Okay, chapter 1, which is the statics overview. So I would like to know the knowledge before the mechanics of materials. So I would like to know within only the statics. Okay, so let's continue on the shear stress and shear strain, and at the end we are going to see the shear modulus. Okay, so we talk that the shear basically is pretty much similar to the axial force or the normal force. The difference is how the force exerted. Okay, so the shear, it will exert it a parallel on the surface. So like for example here, you see that the force is parallel to the plane, okay, to the plane. So we could write down the formulation, and basically the formulations on stress will be the same definition. So we could divide the shear stress. Now it's the V divided by the A. So we can take that as a limit. As we take the area as small as possible, then that is the idea or the definition of the shear stress. And then we could also write down in different schematics. So we could write as a shear average or shear stress average that is acting on some surface area. And then after we deal with the formulations, we are dealing with we call it direct shear. So there are some applications here that we are going to formulate. So we have some pliers and also the metal punch. So when you pull the force on the metal punch, you will get the reaction on the or like a friction on the surface, which is if we accumulate, it will be like this, the free body diagram. So we have a shear forces that is distributed along the metals. So when we push the force, there will be some forces that is going to counter. So it's going to counter the external forces, which is we define these forces as a shear, okay, shear forces. And similarly, when we are dealing with the pliers like this, we exert some forces, we pull or we push the force, and then at the metal hole or the metal inside this circle, we're going to see that there will be, if we look on just one plier, so if we pull the force, there will be some reactions, which is we see that this is going to be shear forces. Okay? And this distributed forces will exert in what we call the shear stress. Okay, now this is differences. Okay, we call the first one as a single shear, and the second one here as a double shear. Okay, so let me explain for details here. So we have a single shear and double shear. So let's say we have like a supplies from some, let's say, some material. So if we pull the material, there will be some frictions in between. Okay, so if we try to make out the free body diagram, we are going to have, so if we pull out this two, there will be some sort of reaction here, in which if we take the first one, the first layer, we put here, then there will be some forces that is going to have like reactions with the second layer, which we define this as our shear. Okay? And as in average, we could see that we are going to have our distributions here, and we define our surface by this length, okay, by this L and W. This will be the length over the area. So within this, we could work out some average value of the shear stress, which we define as a V, defined by AS defined by the W and LS, or we could write here, since there are only these forces, so the V, the shear force, it will equal with the P, okay, because it's equilibrium, and the surface will be LSW, okay, as simple as that, okay. So very, very simple. So we could just see the differences between this normal force and the shear force is only the direction, okay, where it is positions will be, okay, or how it could direct with some specific directions, and the shear will be in parallel with the surface itself. And in more details, if we look on another point of view within this example here, so there are two figures. If you see the figure one, the left one is a lap joint that is bolted, okay, bolted. So you put bolt to join these two. So we call this a lap joint. So it only has a two layer, and then this is the lap joint. We call this is a single shear. Okay, this is a single shear. And this one here, we have 1, 2, and then the middle one, 3. So we have a 3-layer, and both of this figure will be, we are going to pull out with some exerted forces that is defined as P. So this will be, let me write here that this is the single shear. We call the single shear, and this is the double shear. And then if we try to make out the free body diagram for each one of them, we are going to, so let's try to build our understanding or our formulations from these two. So from the left one, this is if we take only one part, so we take this, which means that there will be a shear force on the bolt, okay, on the bolt, at least on the bolt, because that is the one that is keep them jointed together. So we say that we call the sigma F for the bar. This will be 0. So we see that the V1 will equal to P. And for the rod, this is the rod, also 0. So we see that the P now, it will be resulted in two different shear forces, which is phi2 and phi3. Okay? Now, this is what does the single or double means. So single means you have only one shear forces, and the double shear means you have double. You have double shear because you have three layers, at least three layers. One, two, and the middle. Okay. In the first one, we have only two layers, this and that. Okay. So that's how we define the single and double. And because of the symmetry, then one or each one of them will be equal. So phi2 will be equal to phi3 will be equal to p over 2. Okay, that's our definition. For the double shear, we assume that they are going to be symmetrical, and their force will be the same, will be equal. And therefore, the shear stress let me write here, the shear average. So for the bolt here, the shear, let me write B for bolt, average will be phi1 divided by the area for bolt. The area, since we know that this is going to be defined by the diameter B for bolt and diameter pin for the right one, so we are going to use that diameter in our calculations. So this will be, V1 is P, so let me write P, and this will be pi, this will be diameter B squared, and since I'm using diameter, we are going to divide by 4, so 4 is going to be here. Okay. Same thing for the pin. The stress will be this is going to be V2 or phi3. Let me write AP, this is equal to phi3 AP, or we can simplify phi2 or phi3 be with the P over 2. So P over 2, and this is equal, this is dP squared, and this is 4. So we can write this is going to be 2P 4 dP squared. Or if you see from the value itself, we could conclude that if they are having the same forces, if we want to compare, this could be only half of, so the pin will be half of the bolt. Or if you want to use the diameter for single shear, and for the double shear, the tau will be pi over 2 pi r squared. If we want to use the radius, okay, if you want to use the radius. If you want to use the diameter, you could see that it will going to be 4p pi d squared, or the double shear 2p over pi d squared. Okay, and sometimes in some practices or some given problems in the exercise, maybe later we could see, maybe tomorrow I give another exercise. You will see that if we have either or like single or double, the questions will give you some clue. It can be from the picture that you can show. For example, it will show something like this. it will show something like this. If you see something like this, then you could immediately say, oh, that will be double shear. You will use the double shear formula. If you see something like this, only 2 layers, then you are going to use the single shear. Okay? And it will be given. Either it is on the words or in the picture. You see the figure. So that's the direct shear, the single and double. Okay, now let me go through. Okay, next is so next page will be, I will talk about some theory, not really much on a practical side, but it's more on the definition. So this will be about the equilibrium requirements. Okay, so we are going to see what is the pure shear. So let me bring this down first. Okay. So far we have considered, okay, so let me write here, so far we consider the tau average on some surfaces or particular surface. So before we move on, we need to take some time to check the requirements that can be satisfied by shear stresses. So if we have a typical shear stress example, as in this figure, let's say we have this figure here, it is deformable. Okay. So let's say we are going to check or examine all the stresses that is going to be exerted at point A. Okay, so the point A is here. Okay. So we are going to make the body will be deformed. Okay, so we push with some certain forces. So let's say we are going to push here, and if we see the internal schematics from this A, we're going to see that it's moving all the volume. So all the volume will be moving. So this A here, we move all the volume. In our practical applications, in our solutions like we did before, we apply and we assume that it is going to be thin surface. But here, we assume that it has some peak, basically it has some thickness. So when we push this, and if we see whether there are some shear happen inside, it's actually going to have the whole volume. So we have a delta V that is going to be deformed. Okay? So this is what the reality could be. So in practical, in design, for example, sometimes we are only focused on giving details only on the surface for the shear. So we only compute the shear assuming that it is only works on the shear. Like when you have the lap joint with bolt, we only think that the shear that is exerted is only the surface of the bolt. Okay. However, for the whole deformed body, and if we think that the body can be deformed, then what happening is the whole volume is going to be deformed. It's going to be changed. The shape going to be changed by these forces, the shear force. And then we are going to see that when that happens, after deformations, we see that this is going to happen, and then we could draw the free body diagram of this small volume, or we call this is the elemental volume. So if we want to examine this elemental volume, if we could zoom in what is happening there, so we are going to have this. So imagine that there are, so first we see these forces. Okay. Oh, we have this. And then when this happens, there are some forces, if we cut here, there are some forces that's going to be counter. Okay, so if you see, like you pull that, and then this is going to be like a frictions. This is going to be, oh, there will be something over there, and then that is going to be another changes. Okay, there's another changes. Similarly, there will be another changes on the vertical side, because we change the volume. So we change the horizontal. Of course, the vertical also changed. So there will be changes going to be here, and this change is going to be here. So if you see, like this is going to be not exactly a square. So maybe if I draw like something like this, maybe it could be better. Okay, so it could be deformed into something like that. But for our simplification and understanding of the formula, let's just say that this is going to happen. Okay, and the delta. Let's imagine the delta is going to be small. Okay? It's going to be small. So it's like it has some forces, but it's quite small. Okay. And of course, this is what is actually going to happen, and we define this as a pure shear. Okay. So the pure shear in a volume or in a deformable body, we could see that there will be these directions here, which is going to be this will be very important if you are going to learn more on the at least working on something related to engineering design. So we call this as a pure shear. And if we want to satisfy the equilibrium, so let me write the equilibrium here. So this is assumption. Assume thin plate. Delta is very small. And take the sigma f equals 0 and sigma m for the z-axis. Okay, for the z-axis at A will be equal to 0. So we can write here that the sigma will be going to be the stress. So stress Q. The stress Q is the stress on vertically, multiply with T delta Y, or it's going to be the delta V. Okay, the delta V, and multiply with the delta X, and then minus so the delta shear multiply with the thickness, multiply with the distance. Okay. So we see that the tau for Q equal tau for P equal tau. So all of this will be equal for all this tau. So what is the important conclusions? So all the shear will point towards some intersection which we define like this. So they are going to point out into this intersection. Okay. And then the shear stresses on parallel faces or sides are equal in magnitude and opposites in a sense, which means this is we define how this goes to be like this. Okay, so all this tau will be equal. Oh, I forgot to write here. So for the sigma f, this we can write that the delta phi q, the shear force, is equal delta tau q delta ax, and this equal to tau q t delta y. This is how we get this into here. Okay, so it should be the tau point towards intersection or point away from it. So depends on the direction. We could also write like something like this. Okay, opposites in the opposite direction, but we are still considering the tau will be the same. So we call this is the pure shear. Okay, pure shear. Oh, I write here. So this is already in the equation. So don't need to write. So you can just write on the right side. Let me put this over here. And then this one, maybe just put here. This and this. Okay. And this will be shear stress, tau. Okay, now after we observe the pure shear, now we look on the shear strain. Okay, so how to define the shear strain? So if we see the same deformable body, let's say we have here. Imagine that you are going to exert some forces on this, and imagine that what is happening like in between the surfaces, like in the middle here in the body. Maybe you can imagine like a clay or like a Play-Doh. So you give forces on the clay, and then you could sort of see that in between here, if we pull the forces here, there will be some sort of changes which we are going to see. It will move away, and perhaps if you see from the side, it will have something like this. So you have this forces here, and let's say this is the middle part of our body. So this will be the tau, the shear forces, stresses, sorry, and this is going to be the the change in deformations. So when we see this, we are going to have the first thing is the angle changes on this axis. Let's say we have the axis here, so there will be changes here, okay, with some delta, small changes, and also the angle in between of this body. Okay. And we define all the informations, the length and the point A and the delta. Okay. Now, since our original body, it has pi over 2 in angle, which means that the new gamma, this one here, this will be changes from the pi over 2. Okay. So the gamma is pi over 2 minus the theta asterisk. And this is what we can define as a shear strain. So let's write here that the gamma is defined as the change in angle between two originally perpendicular line. That intersects at A. And pi over 2 is the angle before deformation. And the theta asterisk is the angle after deformation. And as in the original or regular strain that we have, the extensional strain, this strain also dimensionless. Okay, also dimensionless. So this is also dimensionless. And also, since the, let me write here, since it is going to be very small, since it is very small displacement, then our assumptions, the tangent, right here, the tangent of the gamma will be equal or approximate the sine of gamma, which equal the gamma itself. So we write here that the gamma equal pi over 2 minus theta asterisk is approximate the tangent pi over 2 minus theta asterisk, or this is going to be equal to the delta S over LS. So usually it will be very, very small, and we could use this tangent approximation. Okay. So sometimes, if it is not defined, like we can use this assumption. And we can use the assumptions that the this strength here very small. We could approximate with the tangent, which we could use the delta over L. But if it requires you to compute all the geometric sides, then you could use this one by one using calculators. Usually taking the sides and then one by one you see using the triangle and so on. If you see how it changed, you can see that we could try the triangle ratio if we know the exact distance, how much is going to be displaced. We can use the ratio of the triangle and then somehow getting into the angle. But if not, and if we just say that okay, it's very small, then we can just use the tangent. Okay. Another thing on the shear is the Hooke's law, which is very identical to our original Hooke's law in the axial forces. So we just change all the normal stresses with the shear stress, and the strain will be the shear strain. Okay. And the E we change into G, which is the modulus force shear. So we can just say that this will be the shear modulus for G. Okay, so it's quite identical. You could just change all the normal force or normal stress and strain with tau and gamma, and E, Young's modulus, we change to the shear modulus. And there will be some connections between this shear modulus and E, the Young modulus, which we can write as this formulations. And I think if we have time, we can discuss more about this. But for now, let's just write the practical formula for the G, okay, for the shear modulus. Okay, let me check what else we taken. Okay, so let's continue here. So I have an example. Since I don't have time to brings the whole picture, so I drew the picture. So the question is very simple. Find the average shear stress on the pins, okay, on A and B. So A and B, it's going to be a pin. And if you see, we have the pin for A that is diameter 20 millimeter. B also have the same diameter 20. And you see that it has the differences on how it's going to be jointed. Okay, so you imagine that the red one here is the bolt, and this is the splice. This is the splice. This is, let's say, the bolt, or maybe jointed with some other techniques. It doesn't specify what it is, but we could see this is going to be 3 layers. Okay, this is going to be 2 layers. So the first one is going to be the double shear. The second one is the single shear. Okay. So sometimes, if you're given this type of questions, you can identify first. Oh, this will be double shear. This will be single shear. Okay. Maybe you could keep in mind. Okay. And then what we need to do is basically, because we have these external forces, right? Because we have external forces, we need to draw the free body diagram out of this whole figure. how to do that is basically because we want to know the stress on A and B. So we need to have at least this bar as our focus, okay? Because we want to have this and this, okay? And then we need to decide what's happening in A, what's reaction on that, what kind of forces, and what kind of forces in B. Since we have on B something that is related to here, right? So let's say this is, let me just write that as C. I forgot to write that C. So let's say this is going to be C. Okay. So we might have something, and because you see that it is given information about this triangle, so we might have something that is related to component of this sine and cosine. Let's say this is another forces that is going to be connected with C. So we need to take this into some sine and cosine components, right? So we are going to have a break. We'll going to see this after break. Okay. Okay, so we back to this equation here. So let me just take this as a double shear. We'll write here as a single shear. And we write that the tau for both of them are 2 of V. This will be 2 pi r squared, or pi with the d squared, and then we'll multiply with over 4. Let me write here V pi r squared. Okay. Now the free body diagram, let me give you the AB bar. So this will be the bar. Let's say that is the bar. So imagine that first we have a reactions on the A, which is in the horizontal and in vertical. And you could first write this as in your assumption. So let's say this is going to be AX and AY. This will be 50 kilonewton. And here is the 2 meter. And that will be 4 meter. Or 4 meter. This is not. Okay, 4 meter. And then we can assume that on this B we have some tension here, which defined by the FBC. Okay. And this FBC will be going to be having 2 components by taking the triangle ratio 3, 4, 5. So this will be 4/5 FBC, right? And this is 3/5 FBC. Right, sine and cosine, right? Okay. So I think everything are available now. So first we write an equilibrium. Let's take the moment. So we could start with the moment on either using the A or B. Both will get the result. So if you start with respect with A, then you will get the FBC. If you start with the B, you will get the AY, right, for the moment. I think we could just write the A, let's say equals 0, and we take this as a positive moment. So we write 50 kilonewton multiply with 2 meter. This is positive, right? And then minus 4/5 FBC multiply with 6 meter equal to 0. So we could get the FBC. So here is going to be 24/5 FBC is equal to 100 kilonewton meter. So FBC is going to be 500 divided by 24. You can count. If I'm not mistaken, this will be around 20.83 kilonewton. So this will be the FBC. We could write another moment for B, but I think we could just focus on the sigma force, then only the normal, because we could explore the horizontal and vertical forces. So we could write the horizontal forces, which is the AX. This will be equal to 3/5 FBC. So 3/5 multiply with 500/24. So it will be 100 divided by 8. So it will be 12.5 kilonewton. And then similarly, take the vertical force equals 0. This will be AY plus 4/5 FBC equal 50 kilonewton. So we could get the AY is 50 minus the 4/5, 20.83. Well, maybe let me write this as 500/24. Maybe more significant is 100. This is 100 divided by 6, around 17. So this will be 33.3 kilonewton, right? So we have AY and AX, and now we need to calculate the forces on A. But to calculate the forces on A, since we have the AX and AY, since they are going to be a vector, remember that they are vectors, so we can take the magnitude of A. So write the magnitude of A is equal square root, okay, and then 12.5 squared plus 3.34 squared. This will be equal to 35.6 kilonewton. Okay, so this is the value of A, and this is we are going to state that this will be equal to our VA. Okay, so we can write the pin at A here. The pin at A is going to be tau A equal VA divided by 2 pi r squared. Since both of them they have the same diameter, 20 millimeter, so this will be, I will write the V as a Newton, so 35,606 Newton divided by 2 pi, the R is 20 squared millimeter squared. Okay, so after some calculations, the Newton over millimeter squared, this will be giving you megapascal. So this will be 56.67 megapascal. And then the pins at B, or tau B, the VB is the FBC here, the FBC, which is the 20.83 kilonewton. So this will be equal to VB. So write down here the VB divided by only pi r squared, the single shear. So 2830 Newton divided by pi 20 squared millimeter squared. This is around 66.3 megapascal, and we get all the stresses on each pin. Okay. Okay, any questions about this? Okay, so basically, to to uh, to take the shear force here, to get the shear force is basically getting all the forces that are accumulated on that point. Okay. Basically, we get usually from the reaction forces, or if there are any extensional forces that is applied in the system, then we are going to include those forces inside the value of the all exerted force. For example, the A, we get the VA, it's going from these AX and AY, and we take the magnitude value of both of them using the vectors, magnitude value vectors. Then we get this. Okay, and then the extensional force that we have on B is we can just use the FBC. Okay. Okay, if there is no questions, so let me continue for one subtopics. Okay, now the next subtopic is about the safety factor. Okay, I'll go right here, or factor of safety. So the safety factor. So in design, if you are designing a structure or equipment, then you need to apply all your fundamental mechanics, all the principles, all the equations to select. Okay, so this will be, so let me write here the important on engineering design. After you get your formulations, your simulations, what you need to do is select the material, or select the materials and dimensions of components. Why we need to select the materials and why we need to measure the exact dimensions? The idea so that no failure occurs. Okay. So this is the idea. Okay. So we want to have a good selection of materials, a good measurement of the dimension. So we design both selecting the materials and measure the dimensions. So that's the idea for the engineering design. So regarding the failure will be related to, we call the modes of failure. So what is the modes of failure? Because failure can be, depends on some options. There are some options that we need to consider, because there will be design, for example, design for strength. So we need something that has maybe higher tensile strength, or maybe yield strength is quite high, or designed for stiffness. So we need to have the modulus that is quite high, because we want the material in elastic region most of the time, okay? Or perhaps we want to have a ductile material. And each one of them, they have different parameters, okay? They have different parameters. And also, like, you could have failure by yielding, you could have fatigue failure because you have a dynamic loads, for example. Or later we will see some failure like buckling. There will be some exceptional failure, something like that. It's very unique. If we have time, we are going to discuss the buckling, because it's related to the bending and compression. But for our restriction in this chapter, we want only discussing. So let me write here, in this course or in this chapter, only strength design, and this will be subject by axial loadings or direct shear. So we are going to restrict our attention only for these two forces. So axial loads or axial forces or direct shear. So based on that, the first idea is about the safety factor. Okay. So the safety factor, as in the as we want to make it into our equations, we could define the safety factor as failure load divided by the allowable load. Okay, so this is going to be like, suppose we are going to design, okay, we are going to design something that is having, so we have load and we have resistance. So if we want to design some structure from some materials, we need to design, and so designing how much R. Okay, it's not R in the electrical current, but this is R for loading. Okay. So designing how much R we need to withhold the load, okay, or L. So the R by definition should be higher than the load. So the structure must be higher than the load. Okay. So the design should satisfy this inequality. Okay. And loads and resistance, they have some factors, like for example, the loads, it is basically factored by the external loads that is acting on that structure. Then the locations, magnitude, direction will be important. And maybe we need to have some assumptions. An assumption is based on different cases. It could be we have some boundary conditions, or we could treat them like a linear behavior property. Okay. And for the R, for the resistance, we could have some assumptions, maybe the strength assumptions, maybe some defect on materials. This is can be important as well. So the quality for from the manufactured materials, and then maybe construction itself has a problem, construction problems, or maybe design problems. So basically so the resistance and load will be affecting how much safety we are going to set. Okay, so that's why, because there are some assumptions, some defects, and maybe there will be some external loads that can be uncertain. So we need something that should be, for example, if resistance is 50 kilonewton and we take a load maybe 49, okay, 49, 50. In mathematics, in our inequality, it could be okay, but in reality, we are not sure the defect, construction design, etc., or we are not sure about the assumption on the load itself. So it could be dangerous. 49 to 50 is too close. So we need to have like a safety factor that we need to multiply, so that we are sure that this should be safe. For example, like you take the elevator. It's written averagely for 10% elevator. I believe if you push 12% or 13%, it could stand. But for safety, for the design safety, it says, okay, we just try to make it limited to 10, because we want to make sure the elevator, it can withstand for some period of time before maintenance. Okay, so imagine if they don't make something like that, and you just go inside and then using the elevator, it will break down, and maybe it will break down in between, right? Maybe before maintenance it's broke, and then maybe it's dangerous. So that's why we need to have some factor that we need to multiply. Okay, so we call, okay, this is going to be the safety factor. So we use this as the failure load defined by the allowable load. Okay. In the practicality for our course, if you see the question that is requiring you to take the safety factor, then it means that you just need to multiply, and then that will be your safety factor. Or sometimes the question will be asked, what will be the allowable load, so that you can design to withstand some forces, external force. For example, let's just see, maybe if we see the previous one here, then it could add some additional questions. Like maybe it's asking, how much does this member need to withhold the allowable stress so that it could not be broken when it is exerted by 50 kilonewton? Okay, maybe this is going to be some forces that you need to compute, and then maybe the question also giving you the yield property, what will be the property for the yield, and then you need to compute before it is going to bend, and maybe before it is going to be failure, and something like that. So it could be the same typical problem like we have before, but it will add some additional informations, like the material property or the mechanical property. And then we need just to multiply for the allowable loads. Okay. So that's the factor of safety. And factor of safety, basically this should be greater than 1. Okay. And the factors can be depends, or so it can be depends on the nature of failure. It also depends by the accessibility. For maintenance, for example, like I mentioned, how we can measure the maintenance for the elevator, and maybe a cost, like how much it will cost if there is a failure. And also the important one is the failure of single member. Okay, so can it be make some impact? For example, if one single member failure, could it be the reason for all structural failure? It could also be something that is important. So one structure bar can be as important as the other bar as well. So that is the safety factor or factor of safety. And another thing to see is, this is allowable stress alert. Let me just write the title. Allowable stress design. So in practicality, for the stress design, we could focus on the yield strength. So basically, it's the same formulation. So factor of safety, the failure divided by the allowable loads. And in this case, if you want to make sure that it is not deformed, then we need to make the yield strength. Okay? So after yield strength, if you remember the material property, after yield strength, it's going to be plastic deformation, which is we don't want to have. Okay? So the allowable stress will be the yield strength of the material divided by the factor F safety that we want. Okay? Or in the stress, we can write in terms of the normal stress or the shear stress. Okay. Let me write. It can be used for the yield strength, or we can use the ultimate, or we can use the sigma ultimate. Okay. So again, it is going to be depends. Okay. Depends on the design. It could be about the yield. It could be about the ultimate failure. But most of our problem will be between both of those. Okay, let's get into this one, or already right here. Let me write, or let me go into the just a small example, and maybe we could see later if we have time. So a small example here is that we have, oh wait, let me go from here. So we have a pin jointed truss. So we call this is a truss figure. So it's subjected to a single force or downward force at joint A. This is P. Okay. And all members have a cross-sectional area of 500 millimeters square. So we assume we have all the same cross-sections area for all truss. And it is giving the information about the allowable stress, the intentions. It is 300 megapascal, and allowable stress in compression that is going to be 200 megapascal. And it's asking how much P should we exert if we have allowable stress for tension and compression as in the given information. So we've given all the conditions. So if we see the truss, we are given the 3-4-5 ratio for the truss 1 and truss 4 and 2. We are given the 3-4-5, which means we are going to include that in our diagrams. Okay, and since this is our external force, then we could take this, the truss 3. We could take this into our observation. So we could write the diagram for the member, or let me just write still here. I don't think we need to make the diagram for the this truss. So based on the ratio of this triangle, so we have, let's say this is the FAB. Okay, we have there. This is 3/5 FAB. This is 4/5 FAB. And this will be another one. This is, let's say this is the FPD. This is the FBD multiplied by the 3/5, right? This is also the same, but this is 4/5. Let me write 3/5 FBD. Okay. Now we have, this is, let's say this is going to be the FBC. Now if we cut only the ABD and we take the sigma moment, so first is we can take the sigma F for X and for Y. This could be 0, and we take the sigma moment. Let's say we take at B, and this will be a positive. So this will be another FBA, FBD, FDB. So what should we do here? So this will be all members. Okay. Okay, so I think we need to have some assumption here for the distance. So if this is L, this is L. So, or maybe if this is L, L over 2, L over 2. 5, so this is 4L. How about I will just write this is going to be equal to the ratio, so 4L. This is 3L, 5L. Same thing with here. I think should be okay if I just write like that. And this one will be equal to 4L, right? I think you could compute based on the force and distance. So is this correct? So 4L I think let's say not B, maybe D. So I will have 8, so minus P, 8L, and plus 3 over 5 FAB, 8L. Is this correct? And FBC, this will be plus FBC 3L equals 0, right? And then we could see from the sigma F, what should we have here is this one, FBC plus 4 over 5 AB minus 4 over 5 FBD is equal to 0, and for the vertical one, 3 over 5 FAB plus 3 over 5 FBD equal to P, right? And here we get I think we can solve using linear equations for this one. Okay. So 4 over 5 FAB minus 4 over 5 FBD. This will be minus FBC. And this will be 3 over 5 FAB plus 3 over 5 FBD. This is equal to P. We can multiply with 5 over 4. This is 5 over 3. Okay. That takes longer than I expected. So FAB minus FBD is minus 5 over 4 FBC. This is FAB plus FBD equal 5 over 3 P. And then let's say we take plus, okay, so 2 FAB is going to be, so 12, this is going to be negative 3, oh sorry, not 3, 15 and plus 20, so this will be FAB, or 2 FAB is negative 5 over 12. Is that it? FAB is oh wait, I cannot do this. Let me write. So FAB negative 5 over 4 FBC plus 5 over 3P. And here we have P. Can we solve this? I think we can solve. Take all L, right? So 3 over 5 or 25 over 5 FAB plus 3 FBC is 8P, okay? And we can substitute the FAB is negative 5 over 8 FBC plus 5 over 6P. Okay, I think we can substitute over there. So 4 over 5. So this will be 120, 40 plus 4P I think I make some, not a mistake, but I just circling around. And it's 8P. So this is 6 FBC. Wait. It's going to be 0. Wait. There is something wrong here. Let me. Anyway. Since I will skip the process and maybe later I will give you the notes on this, right? So if we write and then the whole calculation here, this should be 8 over 3P and it's on tension. This should be 5 over 3P in tension, 5 over 3P in compression, and 5 over 3P in compression. Compression and the tension, it depends on the directions. Okay. So the allowable, it should be 8 over 3 P1 over A1. The A is all the 500, right? 500 millimeter square. So this should be equal to 300 megapascal or Newton over millimeter square. So this should be P1 over 500 millimeter squared. This should be Newton over millimeter squared. So this is going to be cancel that, and the P1 will be 3 over 8 multiply by 500, multiply by 300, around 15,000. Or here, if this in the kilonewton, this would be around this 6.25 kilonewton. And the same thing for the compression. So this is for tension. So for tension, and for compression, we can take the 5/3 P, let's say the 2. So 2 will be, we'll write this is as P2A2. This should be 200 Newton millimeter square, and do the same thing. We're going to get the P2 is 0.5 multiplied with 200 and 500. And if this is in the kilonewton, this is going to be 100. 300 by 200 is 60,000, so 60 kilonewton. So we get the allowable force for both of thrust, for the tension and compression. We get all forces, okay? And since we have these two, we need to take one, okay? So since this is going to be allowable for all conditions, okay, since P1 is smaller than P2, then the P allowable will be the smallest one. It's 56.2 kilonewton. Okay, so I will fix this out, all this component here. I will fix this later. Okay. I got confused here. Let me fix later. Okay, so you should get this structure here for tension and compression. Okay. Anyway, I think we could finish up until here.